We are going to begin our investigation into a new sphere of mathematics called trigonometry. And if you recall last year, we introduced this topic as being the mathematics of the relationship between the side lengths and the angles of a right angle triangle. So we could summarize this as by saying this is simply the mathematics of right angle triangles. RATs for short. Except for this year, we're going to turn everything you think you know about trigonometry upside down. And we're going to share with you a dirty little secret, and that is that trigonometry is not about right angle triangles at all. In fact, it's the mathematics of circles. And so a better word for the mathematics that we're going to be doing right now is circleometry. So that's not to say that what we think we know about triangles and trigonometry, the stuff that we taught you before, isn't right. Because it most certainly is, okay? It's certainly useful. So let's try to recall what we remember about trigonometry from years past. You probably remember that trigonometry had to do with these things called right angle triangles. Triangles with a 90-degree angle is denoted by the symbol. We gave the sides of a right angle triangle labels. Typically, we used little a, little b, and little c. And we reserved the letter C for the longest side of the triangle, which we called the hypotenuse. Or, as I like to call it, the hippopotamus. The hippopotamus. And we labeled the sides this way because when we introduced this funky relationship between the sides, a squared plus b squared equals c squared, the Pythagorean relationship, we used the letters A, B, and C just to keep everything looking shipshape and up to date. So, a squared plus b squared equals c squared. That is the length of a squared plus the length of b squared equals the length of c squared. And finally, we labeled the corners or the angles of the triangle by the sides. So if this is side A, we labeled the angle opposite side A, angle A. And we used the capital letter to denote that. Similarly, capital B is that angle there, and capital C, by convention, was the right angle, that 90-degree angle. Now, beginning last year, we started adding to this picture you have of right angle triangles. We chose an angle, we called it an angle of interest, and then we started changing names on you. We started using these Greek symbols, in this case, theta, for the primary angle of interest in a right angle triangle when working with trigonometry. And then we introduced the idea of trigonometric functions, the sine function, the cosine function, and the tangent function. And in order to define these functions, we started renaming the sides of the triangle on you. So instead of side A in relation to angle A or angle theta, we now said, well, that side lies opposite to the angle of interest, so why don't we just up and call it the opposite side? And the side beside the angle of interest, the side beside angle theta, why not, let's say, adjacent. Let's call it the adjacent side. And because we changed the names of two of the sides of the triangle, let's keep the hypotenuse the hypotenuse. We're not going to change it. But in relation to angle A now, or theta, there is an opposite side, there is an adjacent side, and then there's a hypotenuse. The only confusion that students sometimes had is, well, both of these sides, both the hypotenuse and this side CA, are adjacent. They're next to angle theta. So can you tell which one's adjacent? Well, the hypotenuse already has a name, so it's got to be the unnamed side. And so we went on to define the trigonometric functions as being the ratios of the lengths of sides of a right angle triangle. And so the sine of theta was the length of the opposite side divided by the length of the hypotenuse. Similarly, the definition of the cosine was the length of the adjacent side to angle theta divided by the length of the hypotenuse. And lastly, the tangent function was the length of the opposite side divided by the length of the adjacent side. So before moving on, I'm just going to jot in the labels according to the original naming scheme of the lengths of the sides. So for sine theta, opposite is side A. So another way to think of sine theta is A divided by C, opposite over hypotenuse. I'm just using the original triangle labels here, A, B, and C. Similarly, cosine is B over C, and lastly, tangent is A over B. And why I'm doing this is going to become clear in a second, because now I'm going to look at the other angle. I'm going to look at the complementary angle to angle theta, the angle that we don't have a name here for at the apex A. And I'm going to use another Greek symbol for that, which is very common. I'm going to use the Greek letter phi. Phi, phi, pho, phum. Phi. All right? So similarly to what I did with theta, I'm going to build up the trigonometric ratios with relation to phi. So I'm going to do sine phi, and I'm going to do cos phi, and I'm going to do tangent phi. All right? Because the sine of any angle is always defined as the length of the opposite side divided by the length of the tangent side. And the only complication here is, because I'm looking at a different angle now, is that the opposite side to angle phi seems to already have a name. But that name, adjacent, is in relation to the other angle. So this side in relation to angle phi, this is now the opposite side for phi. What was adjacent to theta is actually opposite to phi. So the trig ratio will be the same. It'll still be opposite divided by hypotenuse. Similarly, the adjacent side to side phi is going to get a little bit of a name change there. It is opposite to angle theta, but it is adjacent to angle phi. And so cosine remains adjacent over hypotenuse, just like it was over here. And finally, tangent to phi is still going to be the same. It's going to be the opposite divided by the adjacent. All right? So what I want you to notice is that these definitions here don't change. Trigonometric ratios are the same for every angle. But let's take a look at what happens when I put the original triangle side labels in. This little letter b doesn't change at all. So sine of phi is going to be b over c. Cosine of phi looks like it's going to be a over c. And the tangent is going to be b over a. And so now maybe you're seeing why I've decided to highlight these two different ways of identifying the sines and cosines of the two different angles. And if you don't see it, let me make it very clear to you. Do you see how the sine of theta, particularly this bit, is related to the cosine of phi? How about the cosine of theta? Especially that. And the sine of phi. Look at that. And finally, do you see how tangent of theta is related to the tangent of phi? It's those relationships that you see between the lengths of the sides of the triangle and the different angles, the angle, let's say theta, and its complement, phi, that are really, truly interesting. And so then you notice that the sine of one angle is the inverse of the other angle. It's the cosine of the complementary angle, which is really cool. If you were really lucky last year, then your teacher ought to have shown you the relationships between the sines and cosines of one angle with the cosines and sines of its complement inside a right angle triangle. And if not, and you're seeing this for the first time, doesn't that make a little bit of sense? And isn't that a beautiful thing to take a look at? I think it's pretty cool. So we've come a long way. If you have got a good understanding of the ratios of trigonometric functions between angles and their complements, then you have come a long way towards getting a grip on and being able to handle what we're about to do. So I've hinted that we're sort of changing the definition. We've played a dirty little trick on you by telling you that trigonometry is one thing, but now it's something different. Don't get me wrong, the trigonometry you learned in the past is absolutely useful. So for example, let's say we have a situation where we've got a flagpole. And you're standing, let's say you're standing, I don't know, here. And let's say you've measured this very, very carefully. And you've measured this as being 4.36 meters. All right. And let's say you want to determine the height of the flagpole without having to climb it. So we want to figure out what that distance is, the height. And we're a little bit lazy, but we know a few things. We know this is a right angle triangle. We know that the distance between us and the base of the flagpole, in other words, the baseline distance, is 4.36. And we can draw this imaginary line. Usually we draw it to eye level and we account for our height, but we'll ignore that for a moment just to make it simple here. And further, we have some kind of angle measuring device here which allows us to determine angle theta as being 42 degrees, okay? 42 degrees. And so we can use trigonometry to pretty efficiently calculate the height of that flagpole without trying to crawl up that flagpole. So the usefulness of trigonometry allows us to figure out the height of the flagpole without having to go up there and measure it ourselves. And we do that by remembering that this relationship between the height, which is really in relation to angle theta, the opposite side, right? It's the opposite side to angle there, yeah? The height, or the opposite side divided by this side here, which is adjacent to angle theta, is equal to this trigonometric function called the tangent, right? Opposite over adjacent equals tangent. And not only the tangent, but the tangent of a specific angle of reference, angle theta, which happens to be 42 degrees. So opposite over adjacent equals tangent 42. We have a little bit more information here. We know that the adjacent side is 4.36, so that goes in the bottom, meters, and h is our unknown, okay? So we set up the relationship between the height and the adjacent side, which we can measure. We've measured the angle of elevation to the tip top of the flagpole, and now all we got to do is sort out this mess. Well, using a little bit of algebraic manipulation, we get quite easily h equals 4.36 tan 42 degrees. And if you work that out in your calculator, you get, what is it? I think you get 9.99 meters, which is, if you're going to round it off to the nearest meter, pretty close to 10 meters, okay? And there we've calculated the height of the flagpole without having to actually climb up that sucker and risk dropping the measuring tape. And so if you've watch the James Tanton videos, then this will all make a lot of sense to you. And if you haven't watched them, I really urge you to go and take a look at them. They really set the scene for understanding, in a human sense, the story behind, the human story behind the mathematics of trigonometry. Because trigonometry is not just this subject that lays in a vacuum. It has a story. So the basis of trigonometry all has to do with astronomy. For millennia, we've watched and observed as the sun moves up and makes its daily journey across the sky. About 3,000 years ago, we began to build a mathematical understanding of how the movement of things like stars and planets and the sun can be so predictable. It starts with observing that the sun rises in the east and throughout the day traverses this big arc across the sky above us. And as we observe it, we observe that the angles change. They assigned a distance to the sun, very arbitrarily as being 1 unit, and because they were astronomically large units, we later came to call them astronomical units, a term that sticks right to this very day. The distance from Earth to the sun, about 150 million kilometers, is known as 1 astronomical unit. And because the sun rose in the east and sets in the west, it led us later on to creating compass bearings that look like that, rising in the morning in the east, rising to its highest height at noon, setting in the west, and then presumably continuing its journey on the other side of the planet. Well, it's not the sun that's moving down the other side of the planet, it's actually the Earth rotating, right? And so now you get a sense of why we are heretically calling trigonometry circleometry. And in watching the James Tanton videos, you also begin to gain the understanding of where the words that we use in trigonometry are coming from. Sine from sinus, which came from jaib, which came from the Arabic translations of the Hindu word ja. And in the Tanton videos, James talks about height, which makes a certain amount of sense. It's the vertical distances, you will, especially if you're talking with smaller triangles, which we're about to. And this idea called overness. Now, I'm not too fond of the word or the expression overness, but think of overness as being just the horizontal distance between where you are, where the observer is, and the tangential line there, okay? So height and overness are what James Tanton uses. We're going to be talking about those in a slightly different sense. And then you get a sense of how the xy coordinates work in a Cartesian plane, right? You know that x is positive here and y is positive here. But if you go to the left of the origin, all of a sudden x's are negative, but y's are still positive. And if you dip below the x-axis, then you know that x is negative and y is negative in this case. And if you go into this quadrant here, x's are positive and y's are negative, right? So it gives you a sense of understanding why plus is always in the top right corner of a Cartesian plane. Has to do with the ancient Babylonian trigonometry. So let's declutter a little bit and let's take a look at the information we have here. And let's consider this situation, this astronomical situation, in terms of the trig that you know and understand. And so that angle of elevation, we're going to call theta. You remember from trigonometry that the side opposite the angle of interest is called, well, the opposite side, and the side beside that's not the hypotenuse is called the adjacent side. And so you remember that sine of theta equals opposite over hypotenuse. But hey, look at the length of the hypotenuse in our new vision, our astronomically based vision and version of trigonometry is. It's 1. And so sine theta, which is normally opposite over hypotenuse, well, if the hypotenuse is 1, then we just get the opposite side over 1, which equals the length of the opposite side. And so we start gaining a slightly different definition of what the sine of an angle is. In a perfect circle that has a radius of 1, that's this bit here, then we now say that sine theta simply equals the opposite side. Likewise, if I'm interested in this distance here, which you know is the adjacent, cosine of theta equals adjacent over hypotenuse, but the hypotenuse is still 1 here, which means that cosine theta is simply the adjacent side. And so that gives us, again, a slightly different definition of sine and cosine, as long as we define the hypotenuse as being equal to 1 unit. In that case, sine theta is simply equal to the opposite side, and the cosine theta is equal to the adjacent side. So let's reconstruct this a little bit and make it a little bit neater and see exactly what we're talking about. I'm going to start with an angle of 45 degrees. You can see that the arc of the triangle that we've created that has a length of 1 can trace out an arc, or in this case a quarter circle on the Cartesian graph, okay? So let's create a triangle because this is about trigonometry. And we are going to want to figure out what that is. And we're going to be interested in trying to figure out what that side is, the length of that side, which is the adjacent side. It might not be immediately apparent, but we can figure out exact values for the adjacent and the opposite side. First of all, do you recognize that because we have a 45-degree angle, that opposite equals the adjacent? In this case only, in a 45-degree angle, that the length of the opposite side equals the length of the adjacent side? You should, because that's the definition of a 45-degree angle. I mean, if we could bring it across here and we'd have the same kind of thing, right? So if that hypotenuse is equal to 1 unit, so what does this tell us? Well, we remember that a equals b, so we could rewrite this, as a equals a squared plus a squared, right? Because a and b are equal. And we could even rewrite that then, even simpler still, 2a squared. C squared equals 2a squared. Let's put some numbers in. We know that c is 1. So 1 squared now equals 2a squared. Let's isolate for a. A squared equals 1/2. And therefore, if I take the square root of both sides, a will be equal to plus or minus root 1 over 2. Root 1/2. Now, root of 1 is just 1. We're only interested in the positive values here for now because we're in that part of the graph. So if I rewrite this, a equals 1 over root 2. This is how I learned it back in high school, back in Ontario. But out here, we like you to get rid of the rational in the denominator. So we're going to rationalize the denominator by multiplying everything by root 2 over root 2, which is really 1 in disguise. And so we're going to get root 2 over 2, 1/2 root 2, as being the value for a. A equals root 2 over 2. And because a equals b, b also equals root 2 over root 2. And now what that allows us to do is create a triangle with exact side lengths. This is root 2 over 2. This is root 2 over 2. We've figured it out Pythagoreistically or something using Pythagoras. And so now if we want to go back now and define sines and cosines and tangents, let's see if we can figure this out. Sine of 45 degrees equals opposite over hypotenuse, which equals root 2 over 2 divided by 1. Well, anything divided by 1 is just itself. So sine 45 looks like equals to root 2 over 2. Now, the difference between this number and the value you get when you plop it into your calculator, I think you get, 0.7071? What's the difference? Well, are they the same, first of all? See, here we have calculated and figured out the value of the sine function without anything else. Plop that into your calculator and you get a really, really, really close answer. The difference is that root 2 over 2 is an exact value. Root 2 in the numerator is irrational. If you try to get a decimal version for that, you will never have an exact number. So if you want an exact value, you keep it in this form here. If you want a decimal value to work with practical trigonometric problems, then you can go root 2 divided by 2 or sine 45. In both cases, you'll get 0.7071. Can we figure out the cosine? Sure we can. Cosine of 45 degrees is equal to precisely the adjacent side divided by 1. So simply root 2 over 2. The same value as sine. And again, if you don't believe me, plop in, go cos 45, and you'll see that it is approximately equal to 7071, the same as the sine of 45. But what we've done is, just using a bit of logic, using a bit of the Pythagoras trick, we've figured out an exact value for 45 degrees. Isn't that great? I think it is. I think we can go one step further and we can figure out the exact value of the tangent of 45 degrees without doing much complicated math at all. Tangent 45 is opposite over adjacent. Well, opposite equals adjacent, so anything divided by itself is a big fat 1. There's your answer. And just like that, applying a little bit of understanding that the ancient Babylonians had thousands and thousands of years ago by looking at the celestial objects rotating around the celestial sphere, we have come up with exact values for sine 45 and cos 45 and tan 45. And in fact, moving forward, you're going to be expected to, if not memorize these values, at least derive them. So why don't you go ahead and find some blank loose leaf, and let's begin keeping track of what we're learning here. What are we learning? We are learning to figure out the exact values of trig functions. Now, we can do that with a calculator, sort of. No, we can't. We can only get approximate values with a calculator. We are learning how to figure out the exact values of trig functions without a calculator. So go find some paper and let's do a summary here. Now, we haven't done some of these values yet, but you can imagine that we're going there. So all we know right now are the trig function values for 45 degrees. Sine is root 2 over 2. Cosine of 45 is root 2 over 2. And the tangent of 45 is 1. Cool. Now, that implies a couple things. It implies that we should be able to figure out all of this stuff without using a calculator. And that, in fact, is where we're headed right now. So let's go take a look and see if we can't figure out sine and cosine and tangent of 0 degrees, because it's really the next logical thing to do, and sine, cosine, tangent of 180 degrees, because that's also fairly straightforward. Let's review what we did here, though. We started off by looking at an angle of 45 degrees. And we said that sine 45 is equal to, using Pythagoras, simply root 2 over 2. Similarly, cosine 45 was equal to root 2 over 2. And for cosine, we're interested in the adjacent, the length of the adjacent side to 45 degrees. And again, using Pythagoras, we know that that is root 2 over 2 and root 2 over 2. That's there, those two heights. So for 0 degrees, what are we looking at? Well, for 0 degrees, we're looking at an angle of elevation that's flat with the horizon. You see here that when the angle is 0, there is no height. There's 0 height. How would that figure out when we talk about sine of 0 degrees? This is 0 degrees in green. Well, sine equals the length of the opposite side. It's actually the opposite side over 1, right? Because the length of the hypotenuse is always 1. But if the opposite side is 0, that implies that sine theta equals 0 itself. And if you go ahead and plop that into your calculator, you'll see that that's exactly true. How about the cosine of 0 degrees? Well, cosine of any angle, you recall, has to do with the overness, that length that James Stanton calls overness, but which we call just the running length or the baseline. And as this arc comes down, then this distance is also 1 unit. And so the cosine now is equal to the adjacent side over 1. Well, 1 over 1 is simply 1. Cosine of 0 degrees is 1. And we're just doing this logically. We're sussing it out without having to do any math. But I encourage you to go and check out, do sine of 0 degrees, do cosine of 0 degrees, and you will see that you get these answers. Let's do one more. We're missing tangent of theta. So tangent of theta, recall, is opposite over adjacent. Well, we know what the opposite side is of 0 degrees. We know that the opposite side is 0. We know that the adjacent side is 1. What is 0 divided by 1? 0. And again, we're just logicking this out. We're doing this through intuition, just by, walking through the steps that these ancient Babylonians laid out for us. Double check with your calculator and make sure that you're getting the same values, because I guarantee you will. So all of a sudden, we've got some values for sine, cosine, and tangent of 0 degrees. So let's go put those in. For 0 degrees, sine theta equals 0. Cosine theta equals 1, and tangent of theta for 0 equals 0. And we begin filling in our table of values for exact values of trig functions without doing any high-level math, without needing your calculator. We can go further. Let's try 180 degrees. 180 degrees. 180 degrees is the angle of elevation straight up. So we're looking at this point right there. And remember, as this arc here travels back and forth, it traverses a line that is 1 unit long. So this distance here is 1. What is the sine of any angle? Opposite over hypotenuse. Opposite over hypotenuse. Well, the hypotenuse is 1. The opposite side is also 1 because we're talking about this side here. As you get bigger, 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 the hypotenuse and the opposite side merge into 1. Sine 180, 1. How about cos of 180? Well, cos of 180 is the adjacent side, but as the angle goes up, 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 the adjacent side gets smaller, smaller, smaller until it becomes 0. So cosine of 180 is 0. And finally, tangent of 180. Well, tangent of 180, remember, or the tangent of any function, is opposite over adjacent. Well, the opposite side is 1. The adjacent side has a length of 0. What's any number divided by 0? Undefined. There is no value for tangent of 180. 180. Again, look it up in your calculators. Plug in those numbers and you'll see that each of those is absolutely correct. 1 for sine of 180, 0 for cos of 180, and undefined. 1, 0, and undefined. Cool. So without doing much complicated math at all, we have been able to figure out most of this table area. What? 9/15 of this table. Just leaving a couple of things left to do. Cos, sine, tangent of 30 degrees, and cos, sine, tangent of 180 degrees. Let's go see how we're going to figure that out. I think it's pretty clear that we won't be able to use this triangle here. So maybe we'll need to figure out and construct a new kind of triangle to help us out. So this 45, 45, 90 degree, remember this is a right angle here. This 45, 45, 90 degree triangle gives us some solutions for 0 degrees, 45 degrees, and 180 degrees. Cool. We're going to have to construct a different triangle now to help us out for the other angles. So to construct the triangle that's going to help us figure out the trig functions for 30 degrees and 60 degrees, let's look at an equilateral triangle. In an equilateral triangle, all of those angles are interior angles, or 60 degrees. That's the very definition, isn't it, of an equilateral triangle? And then let us then cut that equilateral triangle in half. That would make two 30-degree triangles, right? So there's a 30, 60, 90, and here's another 30, 60, 90-degree triangle in the interior there, okay? We're going to borrow again from the Babylonian idea of trigonometry, and we're going to make every side of this triangle equal to 1 unit, okay? So when I cut this in half now, and I'm looking just at this, let's see what we get, okay? Well, up here, I've got a skinny, scrawny angle of 30 degrees. Down here, I've got a rather more robust angle of 60 degrees, and I've got a 90 here, of course. I know that this distance is 1. Well, I also know that if this was 1 unit, then this has got to be a half. So this distance here has got to be 1/2. And that allows me to set up a Pythagorean relationship to give me this. So let's call this x. X is going to be the square root of 1 squared minus 1/2 squared, like that. And if we continue to do the math here, we'll get, well, 1 squared is 1 minus 1/2 squared is 1/4, which is equal to the square root of, well, it looks like 3/4. We can take the square root of the bottom there, so Square root of 4 is 2, so it looks like root 3 over 2. That is an exact value for x, and so let's plop it in there. Root 3 over 2. So now we have the exact values of 3 lengths of sides for a 30, 60, 90 degree triangle. I think now we can figure out the trig function values for both 30 degrees and 90 degrees. Let's make some room first. Let's begin with 30 degrees. Sine 30 degrees is going to be opposite divided by hypotenuse. So 1/2 divided by 1. That looks to be exactly 1/2. Cosine of 30 degrees is going to be adjacent divided by the hypotenuse, which to me looks like root 3 over 2. And finally, tangent of 30 degrees is going to be equal to opposite over adjacent, which is 1/2 over root 3 over 2. And how do you divide fractions? Well, you invert and multiply by the denominator. So 1/2 times, and those will divide out 1 over root 3. Now, as you work your way through the workbook, you'll notice that we don't actually introduce the exact value of tangent for a little while later. I think it's useful to put it here because then we can simply input the numbers and complete our table straight away. So sine 30 is 1/2, cosine 30, root 3 over 2. So 30. There we go. We have just figured out the exact values for sine, cosine, and tangent of 30 degrees. Now, if you have been following closely and you're understanding what we're doing, especially when I showed you this diagram here about how the sine of one angle is the same as the cosine of its complementary angle, then you might have a sense of what values are going to go here and here. Do you think it could be that? What do you think? Let's go figure it out. Let's deal with 60 degrees now. Sine of 60 is equal to, remember here's 60, opposite over adjacent, root 3 over 2. Well, it's root 3 over 2 over 1, but anything divided by 1 is just itself. Okay? How about cosine of 60 degrees? Cosine of 60 degrees would be adjacent over hypotenuse, so 1/2 over 1, which is simply 1/2. Now let's go back and take a look. Sine is root 3 over 2. Sine of 60. Sine of 60, root 3 over 2. Look at that. Look at that. Huh? Isn't that awesome? And I think you'll see very easily and very quickly that the cosine of 60 degrees is going to be 1/2. Let's go back and do. Yep, there it is. And what will the tangent be? Tangent of 60 is going to be opposite over adjacent. And what we do here is invert and multiply the denominator. So instead of divided by 1/2, it's times 2 over 1. Look at that. Simply root 3. Let's put that in. So there you go. By using some very, very simple, intuitive, one might even say grade 7 mathematics, using Pythagoras, we've been able to figure out exact values of all of those angles of right angle triangles just by using logic and intuition. And that, in fact, is the major outcome of this part of trigonometry for you. To be able to not have to rely on a calculator to determine these standard angles, You can figure out sine, cosine, and tangent, boom, just like that, no problem.